In our next two examples, I'll reveal a quick trick to writing down the formula for a function that's growing or decaying exponentially. So our first example involves radioactive strontium-90, which has an atomic symbol 90SR. And so we're given a sample, so we start off with a sample of 100 grams of strontium-90, and the half-life of strontium-90 is 29 years. Now our sample happens to be 50 years old. So our sample is 50 years old, and we need to figure out, so determine how much strontium-90 we have left. Right, our sample's been sitting in the refrigerator for 50 years. I don't know if they put it in the refrigerator or not, but it's in a lab somewhere for 50 years. How much strontium-90 remains? Okay, so we want to model this using exponential decay. So we'll have something like y is equal to a times b to the t. So this is how much remains after t years. And our initial value is 100. So actually, our f of t will be 100 times b to the t. The only thing we have to figure out is the value of the growth factor. So what is the value of the growth factor? So our function again, 100 times b to the t, right? Because when t is equal to 0, we started off with 100 grams of strontium-90, and we know that the half-life is 29 years. So the little trick that I like to do is to just kind of explicitly write out what b is in terms of the half-life. So let's write it like this. 100, and then every so often I multiply 100 by 1/2. Right? Now the trick is that it doesn't happen when t is equal to 1. It happens when t is equal to 50. So to take into account of this, I have to adjust the exponent. So I want to multiply t by something so that this quantity here needs to equal 1/2 when t is equal to 50. So how can I do that? And the answer is to divide t by 50. Actually, if you're wondering why it's 50 and not, or why it's 50 and not 29, you're paying close attention, because the half-life is not 50 years, the half-life is 29 years. So we want this quantity to equal 1/2 when t is equal to 29, not when t is equal to 50. If t equals 50 is some arbitrary number, find out how much is left after 50. To come up with the function itself, we need to use the half-life. So we want this factor to equal 1/2 exactly when t is equal to 29. So as I hinted before, except with the wrong number, we divide t by 29. T over 29. That way when t is equal to 29, we get 1/2 to the power of 1. And we get 100 times 1/2 is equal to 50. And that's the half-life. Now why does this work? Well, basically the number b is going to be 1/2 to the power 1 over 29. Because remember, if I take this to the power of t, so b to the t would equal 1/2 to the 1 over 29. So I'm taking this whole thing to the power of t. And what happens when you have successive powers like this is you multiply the exponent. So this is the same as 1/2 to the t divided by 29. So it does work. It does fit this prescription. It fits this form. You have some number to the power of t. That number happens to be 1/2 to the power 1 over 29. So b is equal to 1/2 to the 1 over 29. And we can see it works because f of 0 is equal to 100 and f of 29 is equal to 100 times 1/2 to the 29 over 29. Now 29 over 29 is 1. 1/2 to the 1 is 1/2. So we get 50. So after 29 years, we have 50 grams. So our function is 100 times 1/2 to the t over 29. So this is how many grams of strontium-90 remain in the sample after t years. So to find out how many remain after 50 years, we just plug in 50 for t. So how much is left after 50 years? So it has to be somewhere between 50 grams and 25 grams, because one half-life has passed by, but not two half-lives. So after the first half-life, there's going to be 1/2 of the initial quantity. After the second half-life, there will be 1/4 of the initial quantity. So it should be somewhere between 25 grams and 50 grams. Now let's see what we get. So f of 50 is equal to 100 times 1/2 to the 50 over 29. So 1/2 to the power 50 over 29 is equal to, so this is approximately 100 times 0.302679331. So f of 50 is going to be approximately 30.27 grams. So that's approximately how much strontium-90 remains after 50 years. And if you want to check, 29 times 2 is 58. If you want to check f of 58, 100 times 1/2, 58 over 29 is just 2. 1/2 squared is 1/4, so you get 25 grams. So after 58 years, you're exactly down to 25 grams. Our next example is with the average home price in the United States. So that we have the average home price in the United States. So in 1980, the average price was $76,400. And then in 2010, the average home price in the United States was $272,900. So let's model this as exponential growth starting at time t of 1980. So let P of t represent the average home price, so this is in dollars, in the United States, t years after 1980. So notice I'm defining what I mean by t, so I don't get confused later on. It's t years since 1980. So when t is equal to 0, that's 1980. When t is equal to 30, that's 2010. So t equals 0 corresponds to 1980, and t equals 30 corresponds to 2010. So now let's take this information that we have from the problem and express it in terms of our function. So p of 0 is equal to 76,400, and then p of 30 is equal to 272,900. So basically, we're looking for a function of this form that satisfies these two data points. So again, we have p of 0 is 76,400, and p of 30 is equal to 272,900. And p of t has to equal a times b to the t. So the p of 0 is what reveals the initial condition a. Now, p of 0, using the formula, would just be a. But we also know that p of 0 is 76,400. So therefore, a has to equal 76,400. And our formula now just looks like p of t is equal to 76,400 times some number b, the growth factor, to the power of t. So now we have to use the second data point, or maybe even the first and the second, to determine the growth factor. And we're going to do something very similar to what we used with the half-life, except it's not going to work out as nicely. So between 1980 and 2010, this is 1980 and 2010, what was the overall jump in prices? So what factor did the prices go up? So 272,900 divided by 76,400. And so what does this equal? Well, that's approximately 3.5719895929. So that's the jump in home prices between 1980 and 2010. Roughly the average price was increased by a factor of 3.57. So it was increased by this factor over 30 years. So we want to kind of dial this guy down by 30 years. So we don't want to use this as B, because this would be B if 1 unit of time was 30 years. But instead, 1 unit of time is 1 year. So to account for that, we'll say P of T, let me just do a new one. So we'll say that P of T is $76,400, and then times this number, 3.5719895929. So that number, again, just a little annotation on the side, was just the ratio 272,900 divided by 76,400. Right, so that's the increase factor over 30 years, and we want to adjust by doing t divided by 30. So that when t is equal to 30, you get 1 for the exponent, and you have this number to the power of 1, which is just this number. When you multiply this number by 76,400, you get 272,900. So that's how it works. So we can, test that out. P of 0, so using this formula, well, actually, one more thing. So the value of B will literally be 2729 over 764. So in this ratio, I divided both by 100 to the power of 1 over 30. So B is approximately that ratio to the power of 1 over 30. So the growth factor is 1.043350766. If you're asked to find the growth factor, this is where you'd want to round your answer. So you can say B is approximately 1.04. I'd play it safe because really you're looking at 4% growth per year. So we don't want to truncate it right here because that's kind of a vague, there's not a lot of accuracy here. 4.335% per growth per year on average gives us a better idea. But we want to, if we're going to round it all, we're going to want to do it here and not here. Because this guy, if we round this and then take it to the power of 1 over 30, it's going to be less accurate than if we keep all the decimals and then we don't round until the final answer. In general, you don't want to round anything until your final answer, because when you start rounding, you're going to get accumulation of errors. So our final answer, we can maybe say P of T equals 76,400 times 1.04335 to the power T over 30. Now let's take a look into the future. What about the year 2020? And let's look at 2030, 2040. So this would be P of 40. So that number to the power of 40, and then times 76,400 gives us the home price in 2020 of approximately $417,164. So that might be what we should expect for 2020. At least assuming constant or steady exponential growth from 1980 to 2010 continues in that trend. So in 2030, so now this is P of 50. So let's take a look at that. So P of 50 works out to be $637,691. And then P of 60, so this would be the projected home price in 2040, assuming that the growth continues at the same rates, $974,795. So by 2040, if this 4.3% inflation continues, which that sounds fairly modest, 4% growth per year in home values. Well, what does that mean? That means your average home in 2010, which was $273,000 approximately, will turn within 30 years will turn to an average home value of close to $1 million.